This research paper introduces a novel approach to speaker-independent speech inversion for estimating nasalance, an objective measure of nasalization in speech. The authors aim to evaluate the degree to which nasalance reflects fine-grained patterns of velopharyngeal (VP) valve movement by comparing it with simultaneously collected direct measures of VP opening using high-speed nasopharyngoscopy (HSN). The paper highlights the importance of incorporating source features, such as glottal activity, to improve nasality prediction in speech inversion systems. The authors propose a temporal convolution-based speech inversion system that learns a mapping from an acoustic representation to nasalance, using source features to enhance performance. The dataset used in this study consists of speech recordings from 8 subjects, with demographic details listed in Table 1. The authors collect nasalance measurements using a nasometer setup, which involves mounting microphones to the top and bottom of a separation plate between the nose and upper lip. The acoustic data is then processed to compute the nasalance parameter, which is a relative proportion of nasal versus oral acoustic output. To validate the nasalance parameter, the authors synchronously collect HSN data from 2 subjects, which provides a more direct and invasive measure of VP constriction. The HSN data is captured at a rate of 1000 frames per second, and the resulting intensity trace is used to assess the accuracy and agreement with the computed nasalance parameter. The authors find that the nasalance parameter is significantly correlated with the HSN signal, and that both match expected patterns of nasality. They also show that incorporating source features, such as voicing and pitch, improves nasality prediction in the speech inversion system. The paper contributes to the development of a speaker-independent speech inversion system that can accurately estimate velar and glottal activity, which has applications in speech therapy, language learning, and speech recognition. The use of nasalance as a ground truth measure and the incorporation of source features are novel aspects of this research, which has the potential to improve the performance of speech inversion systems. The research paper discusses the development of a speaker-independent speech inversion system to estimate the nasalance parameter, which serves as a proxy for velopharyngeal constriction. The system uses auditory spectrograms as input and is trained using a temporal convolution network (TCN) architecture. The nasalance parameter is validated through statistical significant negative correlations with the HSV intensity trace. Patterns of timing for nasality, similar to those observed in Krakow et al., are replicated in the data. The system's performance is evaluated using Pearson product moment correlation (PPMC) scores, showing better agreement with ground truth when incorporating source features as additional targets. The study highlights the potential of this approach for speech applications, particularly in articulatory speech synthesis and research where direct articulatory data collection is challenging. Future work involves training on a larger dataset and further validating the nasalance parameter. This paper presents a comprehensive review of the acoustic phonetics and articulatory phonology in speech production, with a focus on the relationship between velopharyngeal opening and place of articulation. The study leverages a range of research methods, including high-speed nasopharyngoscopy, to quantify the relationship between these 2 aspects of speech production. The authors draw on several key references in the field, including the work of Stevens, 2000, and Krakow, 1999, which provide foundational insights into the physiological organization of syllables and the role of velopharyngeal opening in speech production. They also reference the use of computational models to understand the impact of nasal port area on nasality and nasalance, Bunton and Story, 2011. The paper highlights the importance of considering the gestural coordination at prosodic boundaries, as discussed by Krivokopik, 2014, and the role of temporal information in early auditory representations, Wang and Shama, 1994. It further emphasizes the significance of detecting periodicity, aperiodicity, and pitch in speech signals, Deshmukh et al., 2001. Moreover, the study explores the application of deep learning techniques for speech synthesis from articulatory representations, as demonstrated by Wu et al., 2022. This approach utilizes the MirrorNet model to learn to compute articulatory representations of speech, Siriwardena et al., 2022. The research also discusses the use of acoustic to articulatory inversion, which involves estimating articulatory movements from acoustic signals. This process is facilitated by the use of bidirectional gated recurrent neural networks, Ilya and Ghosh, 2018, and audio data augmentation techniques, Siriwardena et al., 2022. In terms of methodology, the authors employ various statistical and signal processing techniques, such as smoothing functions, O'Haver, 2017, and Hilbert transforms, Feldman, 2001, to analyze the speech data. They also utilize sequence-to-sequence articulatory inversion through time convolution of Su-band frequency signals, Sharababaki et al., 2020. The paper concludes by discussing the implications of these findings for our understanding of speech production and perception, as well as potential avenues for future research in this area.